on a two-dimensional field, an invincible monkey and a tiger play a game in the following way. At the start, the initial points, H0 and R0, of the tiger and the monkey are equal. Then, at each round, first, the monkey moves secretly and unobserved from its current location point, Rn-1, to its next location point, Rn. And the distance between the points, Rn and Rn-1, is equal to 1. At this point, the tiger uses its tracking device, which returns the approximate position, Rn tag, of the monkey. And the distance between the points Rn and Rn tag is at most 1. The tiger then moves visibly from its current location point, Hn-1, to the point Hn, such that the distance between the points, Hn and Hn-1, is equal to 1. This brings us to the main question in this challenge. We have the following main problem. Is there a strategy for the tiger that guarantees that after 10 to the power of 9 rounds in our game, the distance between the tiger and the invincible monkey is smaller than 100? First, we need to observe that if after some rounds in our game, the distance between the tiger and the monkey is at least 100, then the tiger will never be able to shrink the distance to be less than 100. Indeed, if this is the case at some point, then, at the start of each round, the monkey just needs to move in the direction of the vector, which points from the tiger to the monkey. Then, no matter in which direction the tiger moves, the distance between the tiger and the monkey will be at least as the distance that was before the current round. In fact, the best that the tiger can do is to move in the same vector direction as the monkey. But then, the distance will be the same as in the previous round, which is at least 100. Hence, if the monkey keeps using these tactics, the distance will be at least 100 from here at after. Hence, now the question is whether the tiger can guarantee that its distance from the monkey will be less than 100 in all the first 10 to the power of 9 rounds. When trying to answer this question, we always need to take the worst-case scenario into consideration. Where by the worst case, we mean that at each round, when the monkey stops moving, the approximate point, which is received from the tracking device, will not give enough information for the tiger to guarantee that its distance from the monkey is less than 100 for the needed amount of rounds. We will now show that in the worst-case scenario, the distance between the tiger and the monkey can be at least 100 after 10 to the power of 9 rounds. This answers our main problem in this challenge. To prove this, we will show that the output points of the tiger's tracking device can lead to a situation where each 200 rounds, the square distance between the tiger and the monkey is increased by at least 1/2. That is, if dn denotes the distance after n rounds, then, for each positive integer m, we have the following inequality. We then can use the following chain of inequalities to prove that after 4 multiplied by 10 to the power of 6 rounds, the distance between the tiger and the monkey will be at least 100, and this will prove our main result, since, as was explained previously, from this point and afterwards, the distance can be kept to be at least 100 until the 10 to the power of 9 round. Let us show now how the monkey can increase its square distance by at least 1/2 by using 200 rounds. We can assume, without loss of generality, that the monkey and the tiger location points are on the same horizontal line L, and that the monkey is to the right of the tiger. With these assumptions, we can also assume that the tiger's location point is at the origin, and thus, after n rounds, the monkey's location point is at dn for the x-axis and 0 for the y-axis. Let us consider the point P, which is at distance 200 from the monkey and to the right of it, and such that P is at distance 1 from the line L and is also above this line. Now, all the monkey has to do in the next 200 rounds is to walk in a straight line to the point P, where in some scenario, all the approximated points that will be received from the tracking device will be on the line L. This is because each point on the segment, which connects the initial point of the monkey and the point P, is at distance at most 1 from the line L. Since all the approximated points are on the line L, the tiger has no information whether the monkey is below or above L. Hence, its best bet is to walk straight forward on this line for the next 200 rounds, and hence, now the tiger's location point is at 200, and the point P is given explicitly by dn plus the square root of 200 square minus 1 at the x-axis and 1 at the y-axis. Let us prove now that after 200 rounds, the monkey can increase its square distance from the tiger by at least 1/2. We assume from here and after that dn is smaller than 100, since otherwise, we already showed how the monkey can permanently keep the distance to be at least 100. By a straightforward calculation, we obtain that the value of dn plus 200, or equivalently, the distance between the point P and the point 200, is equal to the following expression. Hence, the difference between the square values of dn plus 200 and dn is greater or equal to the following expression. Since dn is smaller than 100, we obtain the following chain of inequalities. This proves the inequality that we needed, and thus our proof is finally complete.